Hi everyone, this is Shreyank. I'm a third year PhD student at the University of Edinburgh, here to present a joint work by the University of Edinburgh and Facebook AI Research, a new split for evaluating true zero-shot action recognition. Let's start with a quick quiz. Which of these is an II? Given it's one of the rarest animals around, and chances that you have seen it are pretty low, it would not be surprising if the answer isn't obvious. Now, let me give you a clue. An II is a long-fingered lemur with rodent-like teeth and a special thin middle finger. Now, given this information, it is much easier to guess which of these is an II. This information is referred to as semantic knowledge, and the problem of identifying an II without seeing any examples before is called zero-shot learning. The availability of large annotated datasets has aided recent improvements in action recognition. Because obtaining thousands of videos to recognize a single class label is unfeasible, academics have turned to the problem of zero-shot learning. Zero-shot learning helps learn relationships using semantic embeddings. Semantic embeddings are either manually annotated or inferred from semantic knowledge utilizing word embeddings for each class label. These embeddings aid in the discovery of relationships between training classes which contain a large number of samples and test classes that have zero samples. It is expected that the training and test classes are disjoint. However, work in video zero-shot learning often uses a pre-trained model to represent videos. While pre-trained models help obtaining good visual representations, they overlap with test classes, and this can invalidate the premise of zero-shot learning, making it difficult to compare approaches fairly. An illustration of the overlap in classes of the pre-training dataset, training split, and zero-shot test split can be seen here. Current evaluation protocol randomly picks 50-50 splits for training and testing. However, there's always some overlap and also chances of an extremely high overlap. We propose a stricter evaluation protocol where there is no overlap at test time, maintaining the zero-shot learning premise. Steps taken to make the split are explained in the next slides. To avoid the coincidental influence of pre-training on zero-shot learning, we now describe the process of creating the proposed TruZe split. To begin, we look for overlapping classes between the Kinetics 400 pre-training dataset and each zero-shot learning dataset. We do this by calculating visual and semantic similarity and discarding classes that are overly similar. Are the labels across classes across datasets exact matches? Are the samples of a particular class in Kinetics visually similar to another class in the zero-shot learning dataset? Are the semantically similar class labels across the pre-training dataset and the zero-shot datasets? We use an I3D model pre-trained on Kinetics 400 to calculate visual similarity. And we use the Kinetics labels to evaluate all video samples in UCF101, HMDB51, and Olympics. This aids us in detecting similarities that aren't always apparent in terms of semantic similarity. Typing a class in UCF101 is detected by the model as using computer, which is a class in Kinetics. To calculate semantic similarity, we use a sentence-to-vec model pre-trained on Wikipedia that helps us compare action phrases and outputs a similarity score. We combine the visual and semantic similarity to obtain a list of extremely similar classes to the ones present in Kinetics. For example, filling eyebrows, a class label in Kinetics, and apply eye makeup, a class label in UCF101, when passed through sentence-to-vec, and we compute the cosine similarity, we find that these are extremely similar. We also confirm the splits obtained by manually checking them. For example, the class pizza tossing was obtained as an unseen class based on visual and semantic similarity, although there is a class making pizza in Kinetics. We looked through examples of the two classes and found them to be disjoint. The first rule we follow to eliminate classes from the test set is to discard exact matches. Some examples of the exact same label being present in both UCF101 and Kinetics are listed here. Classes that predict the same visual and semantic match should also be discarded. Applying eye makeup, which belongs to UCF101, predicts filling eyebrows as the visual match using kinetics labels, and filling eyebrows is also the closest semantic match to kinetics classes. Some other examples include flow gymnastics, jump rope, tennis swing that give us the exact visual and semantic matches of gymnastics, tumbling, skipping rope, and playing tennis respectively. We double check this manually as well. In the manual confirmation, we not only exclude matches but also sub or supersets such as cricket shot and cricket bowling, both of which are UCF101 labels, while kinetics has playing cricket, which in this case would be the superset. We manually do this based on the output of the closest semantic match. There is a subset of baseball pitch videos in the catching or throwing baseball class of kinetics. Hence, we move baseball pitch to the training set. Similarly, all such discarded classes are moved to the training set. Commonly used datasets for zero-shot learning in videos are Olympics, HMDB51, and UCF101. These have 16, 51, and 101 classes respectively. Currently used random splits propose a training test split of 8, 8, 26, 25, and 51, 50 for these datasets. We see that there are 13, 29, and 70 overlapping classes in Olympics, HMDB51, and UCF101 with kinetics. Hence, in our proposed TruZe, we remove Olympics from further evaluation and change the splits of HMDB51 and UCF101 to 29-22 and 70-31. We compare the performance of various models using the random splits shown in green and TruZe shown in blue by using pre-trained I3D visual features. We can see consistent drops in performance whilst using the proposed split. This is expected as none of the pre-training classes are included in our TruZe test split. If we replace the pre-trained I3D features with untrained IDT features, we see that the change in performance is minimal. This confirms that the critical difference between a random split and our TruZe split is the overlap with kinetics, as it only has an effect in this case. However, as state-of-the-art representations require pre-training on kinetics, our TruZe split allows pre-training with kinetics for state-of-the-art performance. To better see this difference, on this slide we are now plotting the same results from the previous two slides, but instead of the absolute values, we are showing the difference between random and TruZe. That is, a high bar means that random performs much better than TruZe. In this plot, we more clearly see that the overlapping classes between training and test set lead to an inflated accuracy with I3D pre-trained on kinetics when using the random split, in contrast to IDT, which is independent of any pre-training model. On the previous slides, all results were on HMDB51. but we observe the same behavior on UCF101. This underlines the problem with the currently used random split, whilst also confirming a new split's value. Next, we report results on generalized zero-shot learning. Generalized zero-shot learning examines a more realistic scenario in which the samples at test time belong to both seen and unseen classes. Similar to the results on the previous slides, there is a big positive difference for unseen classes shown in the green bars. However, for the seen training classes, we expect that the overlap with kinetics is higher for TruZe, and so the performance on the TruZe split is higher than on the random split. This leads to negative differences, as seen in blue bars across all methods. The depicted results are on HMDB51. Again, we see these results are confirmed on the UCF101 dataset. Few-shot learning is another scenario we consider, since the premise is the same as zero-shot learning, except that we have a few samples instead of zero. Again, usually the splits used are random, and as such, the pre-trained model has seen hundreds of samples of classes that are supposed to belong to the test set. We report results on the 5-way 1 to 5 shot. We see that the proposed split is much harder than the standard split. Consistent drops in performance can be seen on every split and for every model. Once again, the same observations hold on the UCF101 dataset. To conclude, we show that currently existing protocol breaks the premise of zero-shot learning due to overlapping classes in the pre-trained dataset. This leads to inflated accuracies. The proposed TruZe solves this issue, and the results show that it is harder in zero-shot learning, generalized zero-shot learning, and few-shot learning. In particular, we see drops of up to 17.1% and 8.1% for HMDB51 in few-shot learning and zero-shot learning, and up to 6.2% and 6.8% for UCF101 in few-shot learning and zero-shot learning. We have released our TruZe split and are excited to see everyone evaluating their methods on this more challenging and true zero-shot setup. Thank you.